Thank you very much for the kind introduction and the opportunity to present today. So before I begin, the terminology of antibody engineering is basically a terminology that we use to define how we create and modify antibodies, the biomolecules that you actually put onto your biosensors. So in actual fact, I've always wanted to be an engineer, but I wasn't very good in physics, so I ended up doing biology. So that's why the closest I could do is basically antibody engineering rather than actual engineering. Right, so to begin, right, I would like to basically explain to you what antibodies are. So for most of you here, you will be familiar with the concept that whenever anyone of us gets sick, we can basically recuperate after a 1 or 2 days rest by ourselves without any medication sometimes. So how does that actually happen? That actually happens basically with our immune system that is actually protecting us and killing off things that are foreign in our body. So the immune system uses proteins that are basically antibodies that basically identify certain targets for diseases specifically and telling the body to get rid of it. Okay? So this is basically how an antibody looks like. Unfortunately, I can't bring an antibody here because it's basically in your body. So if you were to look at it, it actually, from a crystal structure, it actually has a nice Y shape. So normally I get my students in the morning to do the YMCA dance in the lab. So this structure basically is a very important structure. So for antibody engineering, right, we don't actually work with the full antibody molecule. This is actually the full antibody molecule. It's way too big. So what we actually do is we only work with the top part. So imagine if you have a hand, and what is actually moving out to hold on to something is just basically your hand. So basically, your palm. So I don't really need the whole entire arm when I just need the fingers and the palm. So basically what I do is I amputate myself in a way. So I just use the fingers basically because this is the main thing that's holding on and gripping on to something that will be the target. So why antibodies are actually very useful is because in the body, in each one of you right now, what's circulating in the highway of the bloodstream in your body right now is about close to about 1 billion antibodies at a given time. So 1 billion antibodies basically has the potential to bind to 1 billion different targets. So when you look at the applications of antibodies, right, it can actually be used to target different things such as pathogens, chemicals, allergens, venoms, proteins, DNA, and of course, my personal favorite, biological weapons. So, of course, I can't put it up here. Okay. So, these are potential applications for antibodies because they are able to specifically capture and identify these markers. So, if you are developing an application for your sensor, for your biosensor, right, you can actually define your actual application based on using different kind of antibodies that target different diseases. So, the principle of biosensors, basically, I think we've heard about it throughout the whole morning, right? Antibodies falls onto the first category of bioreceptors. So basically, what you actually put onto the sensor defines the actual application of the sensor. So, how do we actually make antibodies? Traditionally, what we do in the lab would be we were to take a syringe with the target protein and some nasty proteins, and we will just jab it onto an animal, and then wait for the animal to generate an immune response. So then we will harvest the antibodies from the blood. But what we are working on is basically fully human antibodies. So as you can imagine, if I'm making fully human antibodies, I should be taking each and every one of you and poking you with a needle, and then taking antibodies from your blood. But with the advent of DNA technology, I don't need to do that. So being in the environment of the university, we have, helpful volunteers, students, who will do basically what we would like them to help out with. So we've basically collected blood from a lot of our local students to generate a collection of antibody libraries. So we have developed so far several different types of antibody libraries, from healthy donors to infectious diseases. So we have actually developed antibody libraries for TB, parasitic infections, and others. So one of the key things is that we don't go into cancer yet because it's actually a very big market out there, but our focus is on infectious diseases. So instead of using animals, right, because currently, if you look at the direction of research, we are actually encouraged to reduce the use of animals in our research. So if you can reduce or replace, you do that. So with this technology, we can actually do that. So what we actually do, instead of using humans, I think Mr. Tan mentioned just now about Jurassic Park. So what seems like science fiction is no longer that fiction. It is possible to do certain things currently. So for what we do is basically, we will take DNA materials from each individual, isolate out the DNA sequences that encodes for the antibody proteins. Then we will introduce these genes into a virus and program the virus to make the antibodies for us. So in this case, basically what we actually have is a small little test tube, about 1.5 milliliters, that contains about 10 billion antibody clones. So basically, we can actually generate each and every one of your own immune system in one test tube and just keep it in the freezer in the lab. So we have actually gone through that process over the last few years to develop this. So what does all this engineering mean to you? So if you were to, I'm not sure if most of you watched Jurassic World recently, if you were to look at the plot of the movie, if you can make a dinosaur, why stop there? Why not make a better dinosaur? So that's how they designed the Beta Raptor, right? So we can now make antibodies. So why should we stop at just making antibodies? Why not make better antibodies or useful or customized antibodies? So in this respect, right, we look at the technology beyond generating antibodies, but we are looking at how we can actually improve or modify the antibodies for customized applications. So, for example, the first thing that we can do is we can do affinity modifications. This basically means we change the way or the strength of how the antibody binds to a target. We can either make it bind, basically hold on to the target stronger, or to hold it less. Because in certain applications, we do not want something to stick too hard onto the surface. So we can actually modify and customize the application based on what we need. So other characteristic modifications include thermal stability, solubility, and durability. This is actually very important in terms of application, especially for thermal stability, because if you were to look at, I think the slide by Dr. Pavu just now about the camel going into the field for point of care testing, cold chain transfer of proteins is a major challenge because proteins tend to degrade at high temperatures. So for certain antibody structures, we can actually modify the structure to make it heat stable, so it can withstand higher temperatures and last longer and maintain the stability. So solubility is very important because we need it to be able to be produced at very high yield so that it can be replicated with less, I would say, less problems for production. And durability. Durability is in the sense of how it responds in different pH. We can actually cater the antibodies to work at different pH. And my favorite, of course, is the different sizes. So basically from this chart, right, you can see this is basically our building block, this small molecule. So from here, right, we can actually modify and do whatever we like to basically increase the size of the protein and also the function of the antibody. This basically allows from a monovalent binding to a polyvalent binding. So in some cases, this might be very useful. But most of these applications are mainly meant for therapy rather than for diagnostics. So why is antibody modification actually useful? Because when you look at sensor development, I mean, I know a lot of you are talking about the noise factors from your readers and the physics kind of noise. But in terms of what we basically work on is basically reducing the noise of binding. So we are very concerned about non-specific binding of a protein to a target in a assay development. So basically, we can actually try to reduce the noise level because in some samples, biological fluids, you have other proteins that are present which can cause non-specific interactions with your sensor. That gives you a false positive in that sense. Of course, next one is on sensitivity. Smaller fragments basically means you can put more antibodies onto the surface. Presentation. Presentation means the way the antibody is oriented on your sensor plane. It's either going up where it's accessible or it's lying down when it's not accessible. So having everything standing up is actually very useful. And of course, reproducibility. The problem about using animal antibodies is what happens when the animal host dies. You basically lose your antibody production system. Therefore, you will have to re-customize, re-optimize your entire system to fit the new antibody that you're going to use. So if you're using DNA technology to produce the antibodies, you can constantly produce the same antibody all year round, regardless of anything, because we are using bacteria. And of course, there's a value add where we can do bispecificity, meaning multiple targets, or even create hybrids with DNA. So this helps with signal amplification. So when we look at attachments on surfaces, right, what kind of modifications that we can actually look at? So in our lab, we focus more on paper. We do a lot of attachments onto just nitrocellulose paper because it's cheap. So what we can actually do with conjugate attachment of antibodies to surfaces is basically either by chemical conjugation or by enzymatic conjugation. So in our lab, we focus more on enzymatic conjugation. We use natural enzymes to basically cleave proteins at certain positions to allow them to attach itself covalently onto a surface. So we prefer to use enzymatic conjugation because that's where our understanding is, number one. And of course, it allows us site-specific conjugation. Because using chemical conjugation, the orientation of the antibody on the surface of your sensor cannot be controlled because it binds based on the accessible groups. But in an enzymatic conjugation, it identifies motifs for it to attach. So by introducing the motifs using recombinant technology, we can now program the antibodies to stick in a specific manner. And of course, why good orientation is important because it allows greater affinity because more antibodies are positioned in the right way. Reproducibility because we can actually control the conjugation process onto the surface. And of course, to increase sensitivity when you have more antibodies. So when we look at the workflow considerations, right, for sensor development or biosensor developments, what can actually recombinant antibodies do for you? So I like to look at the concept of Lego figurines. So if you take a trip down to Gurney Plaza or something, right, you can find at the Lego shop, there's a console in the middle where they have all the different bodies, and different legs, and different heads. So you just have to mix and match, and then you get a nice Lego figurine. So much like how this concept works, right, it can actually work in a biosensors application. Consider that the body and the legs are basically part of your sensor, and the head is the antibody. So basically, by swapping the heads, right, we can actually define different applications on the same platform. So basically, you can have one platform that can actually be used to detect multiple diseases. This is just basically by swapping the antibodies that you actually attach. So for us, right, if we were to, what the ideal scenario or the hope is that we want to have a universal pipeline system where we can actually modify antibodies to ensure continuous attachment of antibodies to different surfaces using the same conditions and concept. Therefore, it allows for a more streamlined process for production. So another main thing that we want to highlight here is that you have all your different types of sensors, but if your antibody basically is modified, you can actually now not just have different antibodies onto the same platform, but you can look at it from the other point of view where you can have the same antibody on multiple different platforms. Therefore, your actual value of the platform increases tremendously because when you set out to design something, you will have an idea of your target application. But what can actually happen is that with certain modifications and using a recombinant technology, you can actually now expand the scope of application for your sensors. So I just want to tell you that I will end here because I realized that my talk is the last talk before lunch, and I'm sure this is not the best time. But anyway, I just want to finish off by telling you that with DNA technology, the limits of your the application of your sensors is now seamless. You can basically expand your applications to whatever applications you are actually targeting. And the beauty about DNA technology is that you can actually now create what you are actually imagining in your sleep. So with that, I would like to say thank you, and that's all from me.